Okay, so we're on. I know last time we left off, we had just finished talking about the epiphyseal plate or growth plate, and that's slightly out of order. That was going ahead a little bit in the chapter. It doesn't matter, it's all in there. So I'm going to go back a section or two and talk about embryonic ossification, which is the development of our skeleton in utero. So when we are embryos developing, so I'm going to go to my first whiteboard and just write the word ossification. Just means the formation of new bone tissue. That's different, as we pointed out last time, from calcification. Calcification is the depositing of calcium into a certain area. Calcification is an ingredient, a necessary ingredient for ossification to take place. There's two major types of embryonic ossification, and I'm just going to list them, numbers 1 and number 2. First one, this should be in the order of your book. It's called, and that's a D, endochondral ossification. I'm not going to write every single thing that I say in order to save time, but you can record this or you can watch my recording as often as you'd like. This word we know what ossification means, formation of bone or bone tissue. Endochondral means within cartilage. So we are starting with a hyaline cartilage model in this form of embryonic ossification. And bones all bones in the human body develop this way, except for, that's supposed to just be an N, except for, so you can just take it to mean all bones except for the cranial plates, the facial bones. So most of the bones in the skull, for some weird reason, not the mandible, but the bones in the skull and the parts of the clavicle. So you can just think skull and clavicles develop this way. Sorry, all bones except skull and clavicles. I just gave a lecture down at Rowan, and their textbook goes in the opposite order. Their textbook gives the intramembranous ossification first. That's why I'm backwards here. So we have all bones except, I'm going to write skull, clavicles. And we just defined it as occurring, it's ossification occurring within a cartilage model. So what I'm going to do is draw a quick picture and go through the steps with you. And I'm going to use blue at first because to designate that this is a cartilage. When we are in utero developing embryologically, we develop this hyaline cartilage skeleton looking system. It's not bone, it's cartilage. And the bones, the cartilage looking bones tend to look kind of cartoony. They're not very well formed. They're very basic shapes. So we start with this hyaline cartilage model inside of the uterus, and the bone actually ossifies from this model. And here's really what happens. In order to make bone, there's basic ingredients. I think I said this last time. We need a blood supply because we need calcium. The blood actually brings calcium to the area, and other minerals as well. Calcium's the major one. So we need blood supply, we need calcium. We also need osteoblasts, active osteoblasts that are secreting that organic osteoid part of the matrix. So here's what happens in this endochondral ossification. We get blood vessels, we get more vascularization in this area of this hyaline cartilage model, sort of the middle of that cartoon bone. And those blood vessels are going to bring nutrients as well as calcium minerals to the area. Mesenchymal cells, which are those embryonic connective tissue stem cells, they give rise to, they differentiate, your book doesn't say this step, but they first differentiate into osteoprogenitor cells, which give rise then to osteoblasts. So mesenchymal cells give rise to, I'm just going to draw some osteoblasts. Those are the immature bone cells that secrete osteoid, or that organic part of the bone matrix. And they start secreting. Those new osteoblasts start doing their thing. They secrete osteoid in this area. The calcium from the blood that's deposited in this area mixes with that osteoid, and we get a hardening of a true ossification of tissue in this area. And it starts sort of on the outside of the shaft of this cartilage model, like I'm drawing. Hi, Alicia. Sure. Yeah. Let me find your name on the, there you go. You're recorded. So we get ossification starting here. And then very shortly after that, we get the sort of the carving out of a medullary cavity in the middle of this model. So well, what happens is cartilage cells on the interior of this model, they blow up and die, sort of like in the growth plate, the epiphyseal plate. They enlarge, they swell, they die, they leave cavities in this space. Also, osteoclasts participate and start to carve out a hollowing in this area. That's going to become the medullary cavity. So that's sort of step two. And ossification proceeds sort of from the outside collar around that I've drawn here and moves interiorly. And we always have spongy bone, trabeculi. So I'm going to draw these little spicules. That always precedes compact bone tissue whenever we make new bone tissue. So just to reiterate, we start with this hyaline cartilage model. We get a blood supply that brings calcium. Parenchymal cells or mesenchymal cells in the periosteal region, they differentiate into osteoblasts that secrete osteoid. It mixes with the calcium, and we start to get hard stuff, hard bone tissue being deposited in this area. Spongy bone develops prior to compact bone. Then later, this is in sequential order, by the way. This is called an ossification center. So this is the primary ossification center here. Then we get secondary ossification centers in the epiphyses. So after the primary ossification center ensues and begins to do its thing, we get secondary ossification centers appearing in the epiphyses. And that's basically the same process occurs, meaning blood brings in calcium, calcium is deposited, osteoblasts in the area start to secrete osteoid, that mixes, we get a hardening, and spongy bone starts to develop. The difference, one of the main differences worth noting here is bone in the secondary ossification centers really work from the inside out, not from the outside in, like in the primary ossification center. So we get secondary ossification centers making spongy bone in the epiphyses. That spongy bone will remain in our long bones throughout life, even though it gets remodeled throughout life. But the area of the diaphysis, this will eventually convert to compact bone, which happens later. And finally, there's a small thin layer of compact bone enclosing that spongy bone on the epiphyses. And this a thin layer of hyaline cartilage continues to exist right here, covering the epiphyses, and that becomes articular cartilage to enhance articulation at a joint with another bone. So that's those are the basic steps of endochondral ossification. The second form of embryonic ossification is called, number 2, intramembranous ossification. And that means inside of membranes, we get bone forming. This would be bones of the skull and clavicles. And technically, the bones of the skull, except for the mandible, which uses endochondral ossification. This one's a bit simpler than the first one. It's not quite as sophisticated. We do not start with a hyaline cartilage model. What we start with are membranes, fibrous membranes. So I'm just going to pick a color that's different than blue. There's an ossification center, a primary ossification center, it appears in fibrous connective tissue, not in cartilage. So here's some fibrous connective tissue looking like areolar connective tissue, but this is embryonic, and we've got mesenchymal cells in this embryonic tissue that differentiate into osteoblasts. That's chemically signaled, if you're curious. So these cells become osteoblasts. And like I said, your book actually skips a step here. They actually give rise to osteoprogenitor cells, which then give rise to osteoblasts, but that's okay. Then the osteoblasts in this area do the same thing. They secrete their osteoid. We get an infiltration of vascularization for nutrition for those osteoblasts, as well as calcium being deposited. So the recipe for building or synthesizing new bone tissue is always the same. We need a blood supply, we need a calcium supply, we need osteoblasts that secrete that organic part of the bone matrix called osteoid. When the osteoid and calcium mix, that hardens the material and it creates that bone tissue. And that hardness not only isolates an osteoblast like this, it also tends to encapsulate vessels. So that hard tissue encapsulates blood vessels, and that's how we get the nature of bone being so vascularized, is from blood vessels that were there prior to the hardening of that matrix. So that's it. That's a nutshell version of the intramembranous ossification, which are two that you can read the details in your textbook. I pretty much translated it fairly quickly, but also fairly completely. But we need to get on to another topic, and that is, we talked about growth of a bone in length. That was the epiphyseal plate / growth plate discussion last time. Now we need to mention growth of a bone in width, which is termed appositional growth. Sometimes I say apositional growth, just to remind students that it begins with an A. Correct pronunciation is most likely appositional growth. This is how a bone grows in width. It's more complicated than your book describes, but I'll try to stick to the easy version. It's fairly straightforward and simple. If we start with a bone, there's the diaphysis of a bone. Here's the medullary cavity. When a bone grows in width, we have a high rate of osteoblast activity on the outer surface of the bone underneath the periosteum. So this is that coarse connective tissue covering the diaphysis. Just under this jacket of connective tissue, osteoblasts secrete new osteoid at a high rate. And they have a blood supply, and that blood brings calcium and all those necessary ingredients. We're just sort of truncating this explanation a little bit. So that's what provides for the growth out here at the outer surface in width. At the same time, there's activity in the medullary cavity in here. And on this surface, we tend to get osteoclast activity. I'm making them big, sort of ruffled shaped cells because that's what they look like. Osteoclasts, which dissolve bone tissue, widen the medullary cavity. So we end up with something that looks like this. So the medullary cavity did get larger in diameter, but the bone wall got thicker than the medullary cavity got wider. So what we're saying is this, osteoblast activity on the surface of the bone outpaces osteoclast activity at the medullary cavity surface. That's why we end up with a thicker walled bone. So osteoblast activity, I'm going to put on the surface, the outer surface, outpaces osteoclast activity at medullary cavity surface, just under that endosteum. And that describes pretty much how appositional growth occurs in a bone, thickening the bone as well as making it larger in diameter. Which brings us to the next terminology of bone remodeling. So all of us right now in this meeting are fully grown adults, physically fully grown adults. So we're not growing in height necessarily anymore. That doesn't mean that we're not making bone tissue. In fact, a healthy individual makes new bone tissue throughout their life. And when adults are fairly young and healthy, that osteoblast activity runs at about the same pace or rate as osteoclast activity. So our bones don't necessarily get considerably larger or smaller, but we are still replacing old bone with new bone. And it's something like, it depends on if we're talking about compact bone or spongy bone. Compact bone replacement is something like 5% on average a year of our skeleton. Spongy bone is greater, especially in certain areas. It can be up to 20% replacement per year. A different bone may have different rates of remodeling on the same bone, depending on the stress points and the demands put on certain spots of that bone. I am going to write these two terms under, I just described what bone remodeling is. These two terms I want you to be familiar with. Bone deposition. That refers to the depositing of new bone tissue by osteoblasts. We've described that several times. And then bone resorption is the dissolving of older bone tissue or of bone tissue in general by osteoclasts. We have described bone deposition quite a few times now, so I'm not going to go through those steps again. Blood supply, calcium, osteoid, osteoblast, new bone tissue. Bone resorption, I'm going to explain really quickly how that occurs. Here's the edge of a bone. I'm not even going to draw the medullary cavity just to save time. Osteoclasts tend to patrol the surfaces of our bones, and they attach themselves to a bone surface. I'm going to exaggerate that because they're obviously not quite this big, but let's exaggerate this cell. This is an osteoclast. It's huge because it's made of the fusion. It's made from the fusion of several monocytes, white blood cells. So it's a multinucleate, very large cell. It has this ruffled surface, and it patrols our bone surfaces, attaches to them, and really seals it off, almost like a leech on the skin. And this I'm just going to draw an arrow. This osteoclast secretes digestive enzymes that dissolve collagen. That's the organic part of bone matrix. And then it also secretes acids that dissolve the minerals. So it affects things like calcium. It's called hydroxyapatite, which is calcium and phosphorus put together. So I'm just going to put calcium out here. What it does with, especially with some of the organic components, but let's just follow calcium. Calcium then is free to leave the bone because the bone is being dissolved, the matrix is being dissolved. The calcium enters the osteoblast like this in a vesicle, and then the osteoblast spits out what's inside of the vesicle on the apical, so the other side of the cell. So I'm just going to draw. Calcium has made its way through that osteoclast cell into the interstitial fluid, which has blood vessels in it, and now that calcium can enter the bloodstream. So when osteoclasts break down bone tissue, like I just described, what that does is it liberates the calcium inside of the bone and puts it in the bloodstream where it can be used by other cells. That describes the whole process of bone remodeling, deposition and resorption. Now we're going to talk about the control of calcium homeostasis in the blood. So let's get on to that topic. I'm just going to write 99 because it's a nice round number, but technically over 99% of the body's calcium is stored in bones. That doesn't leave very much left to be in our cells as well as in our bloodstream. A very, very small, less than 1% of, it's like 0.001% of calcium in the body is actually in the blood at any one time. So I'm going to write that 0.001% in blood. That doesn't seem like even worth talking about. However, it is. This amount, which is like 9 to 11 milligrams per 100 mils of blood, is strictly regulated. That means if the amount of calcium in the blood drops even a little bit, it can actually be dangerous to the body. So we're going to talk about that marker, that regulatory factor of blood calcium. Before I do that, this is worth listing. Why do we need calcium in the body to begin with, or in the blood to begin with? Ionic calcium is the most used mineral in the human body. And I'm going to give you a short list of what it is used for. The list is longer than this, but let's just name 4 or 5 of them. All muscle contraction uses ionic calcium. So every time you move a muscle, every time your heart beats, calcium is being used. Nerve impulse transmission. So every time a nerve cell fires an impulse, guess what? It has to have calcium in order to do that. Next, I'm writing hemostasis, which is the enzymatic process of blood clotting. Every time your blood clots, if you're bleeding, that process of clotting that blood needs calcium in order to proceed. So it's a lifesaver in that respect. Cell division. When our cells divide mitotically, calcium is also used or required. Gland secretion. The process of secreting a substance typically uses calcium ions in order to complete that process. So calcium, we don't make calcium. We have to ingest it. Most of you know that. we can eat calcium all day, all we want. The key is to get that calcium absorbed in the small intestine. So we need to ingest it in our diet, and then it has to get across the wall of our small intestine into our bloodstream. That's when it counts. So I'm going to write calcium is absorbed. I woke up at 5 o'clock this morning because I thought it was 6 o'clock, so I'm a little tired. Absorbed. Calcium is absorbed in the small intestine. And what enhances this process is vitamin D. The active form of vitamin D, which is called calcitriol, really regulates this absorption process. All right. I'm just going to call up a new board. I'm still sort of on the same topic. Calcium, blood levels of calcium can also be hormonally regulated. I'll explain exactly how that's done. Parathyroid hormone, and I'm going to abbreviate that. I want you to know what PTH stands for. But PTH, parathyroid hormone, is the main #1 hormonal regulator of calcium levels in the blood. And here's how it works. Your parathyroid glands are located deep within thyroid tissue. Para just means around thyroid, but technically they're embedded in the thyroid tissue on the posterior side of your neck, on the back of your neck. So they're separate glands from the thyroid gland, but they're located inside of the thyroid gland. Here's what happens. When blood calcium levels drop, decrease, PTH is secreted from parathyroid cells. We have more than one parathyroid gland. Most people have 4. It varies from individual to individual, but by and large, most of the population has 4 of these parathyroid glands. When that PTH is secreted, it raises blood calcium levels in 3 ways. So I'm going to say PTH increases blood calcium levels by colon. First, that hormone increases osteoclast activity, stimulates osteoclasts to go to work. And we just discussed that when osteoclasts dissolve bone matrix, it releases calcium into the blood. That raises blood calcium levels. The second mechanism, PTH enhances the effects of calcitriol, which is active form of vitamin D. And so what that does is it enhances the absorption of calcium in the small intestine. Technically, that takes place in the ileum of the small intestine, which is the distal portion. And third, PTH, this hormone, signals the kidneys. So when we absorb, if we absorb more calcium that we've ingested, that also raises blood calcium. Then PTH also signals the kidneys to decrease calcium excretion in the urine. So what it tells the kidneys, when you're forming urine to get rid of out of the body, don't put as much calcium in the urine. And if we hold on to that calcium, that also raises blood levels of calcium. So those are the three main mechanisms that PTH uses to raise blood calcium levels. So you get it now. Bones act as a storage site for calcium, and it's drawn out of the bones when needed through this mechanism, largely of PTH, or parathyroid hormone. Before I leave the hormone discussion completely, this hormone, serotonin, which is associated with mood and satiety, this is a hormone. It also helps regulate our sleep cycles, along with melatonin. Serotonin is secreted when we eat food. And what serotonin does when it's secreted into the blood, it actually interferes with osteoblast activity. So let me write that out. So we slow calcium deposit when serotonin is present. I'll make sure you understand the connection here. So this is a theory of why serotonin is secreted, and it's known scientifically that it interferes with osteoblast activity. So we don't deposit as much calcium when serotonin is being released. That leaves calcium to be available in the blood. I'm writing response of mechanical stress. I meant to write on, not of. The short story to this is stress on bones is actually a good thing. Let's dive a little deeper into that. There is a scientist whose name was Wolf, and he came up with something that's now called Wolff's Law. And it just states basically what I said. Bone grows in response to the demands that are put on it in the specific areas where that stress is or the demand is. So this explains things like, I'm just admitting more students here, that's why I'm pausing. This explains things like why, if you're right-handed, your right arm is slightly larger than your left. And that's really, really visible in, for example, a professional tennis player. If they're right-handed, their right arm is highly developed relative to, muting my new participants here. More people are dropping in. All right, so this explains, I'm just going to put RL handedness. It also explains things like exercise. For example, weightlifters' bones are much larger and thicker than non-weightlifters. That's due to the mechanical stress or demand put on the bone. Let me give you a quick picture, and then I'll explain to you what's going on the microscopic level. For example, if this is, say, the neck and the head of the femur in the hip, that's the ball of the ball and socket joint. We have muscles, as you know, that attach by the way of tendons to all sorts of areas around the hip. And every time we walk, jump, run, those muscles pull on those attachment areas, and that's the stress of that causes those areas to be prominent and grow. So if you look at a fetal skeleton, the one that that hyaline cartilage model, even after it begins to ossify and become bone, that fetal skeleton doesn't have near the articulation points or these bony markings that an adult skeleton has, or even a child skeleton, from the stress of walking, jumping, gravity, all of those things cause the bone in those areas to grow, the bone tissue. Now, on a microscopic level, here's what's going on. When an area of bone tissue is stressed, say from a tendon pulling on it, that's an example, in the tissue, first, there is an increase in electrical activity of the minerals. When we stress a bone, it energizes electrically the minerals within that bone tissue. It is scientifically theorized and accepted that that increase in electrical activity attracts and also energizes osteoblasts to that area. And then the osteoblasts, as you know, they secrete osteoid, which when mixed with calcium makes hard bone tissue. I'm just going to write osseous tissue. We also, the theory is well accepted, not only because that's been shown to what it happens in active individuals at certain places on their bones, but also from the lack of these prominences on a fetal skeleton or somebody who has been sedentary, say bedridden for months or even a year. These prominences tend to disappear. So somebody who's bedridden, their femur might look something like this and something like this. Even though the muscles might still be attached at these places, those muscles haven't been pulling and causing stress on the bone tissue. So we not only get growth at an area where it's stressed, we get degradation or hypertrophy of tissue when there's not stress put on it. So I always tell my students, think of that the next time you take the elevator rather than the stairs. By taking the stairs, you're actually increasing the good stress that's put on bones and increasing osteoblast activity. So physical stress, the message is actually good. It increases bone matrix and new bone tissue in those areas. Let's go to black, you can see it better. Other dietary hormonal factors. I'm going to try to go quickly so I get to all topics, as many as I can in this chapter. So I'm just going to go down, I'm going to make a laundry list here. Vitamin D3. So vitamin D is necessary for proper bone protein synthesis in bone tissue. The pathway, which I described when we studied the integumentary system, is this. Sunlight hits the skin produces an inactive form of vitamin D3, which is technically a hormone, by the way. That inactive form called cholecalciferol goes to the kidneys where it's converted with the help of PTH and serotonin. It gets converted to the active form calcitriol. That's a long pathway. Vitamin D3, after it is converted in the kidney to calcitriol, it enhances, that's supposed to be CES, it enhances calcium phosphate absorption in the small intestine. So we eat calcium, but we need to get it into our bloodstream, and it's vitamin D3 that helps with that process. Vitamin C, amongst a million other things that vitamin C does for the good in our body, is it is necessary for collagen synthesis. It also assists with osteoblast differentiation to some degree, but most of it is for the collagen in that osteoid organic matrix. I don't know if any of you have ever heard of scurvy. It's not talked about very much anymore because it's not that common. Scurvy is a disease, SCURVY, and that's a vitamin C deficiency. And when we have that vitamin C deficiency, it causes for a loss of bone mass. And it used to afflict people, obviously, who were out at sea for a long time and didn't have access to vitamin C, to ascorbic acid. And so sailors, hundreds of years ago, used to pack their boats full of limes and lemons in order to avoid getting this disease, this deficiency. Vitamin A, which we know is found in things like carrots and egg yolks, that increases osteoblast activity, as well as other benefits in the body, neurally in the retina of the eye, but we're just talking about bones now. Vitamins B12 and K. These vitamins also increase other protein synthesis in bones other than collagen. So I'm just going to say increase protein synthesis. And finally, I'm going to talk about two other hormones. I don't have my Marib textbook at my side at this moment. I know that they mention growth hormone. I forget if they mention really how growth hormone works. This is a hormone that's secreted by the anterior pituitary in the brain. It influences bone growth in children before puberty. So that sort of slow, steady growth that children progress upon from birth to their teens, growth hormone is the major factor influencing those years of bone growth. When I said I'm not sure if they tell you this or not, I'm just going to mention how this works. This hormone is released from the anterior pituitary of the brain. What it really does is it tells the liver to release something called insulin-like growth factors. Those can be released from the liver or bone tissue itself. And it's really those IGFs that have the major effects on the bones. So this is actually, growth hormone technically is a precursor to another hormone that influences bone growth in children. Sex hormones, that just means estrogens and testosterone. They're called sex hormones because in their amounts, they dictate what gender we are. So estrogens, actually our genetics do that, but they are in different amounts in different genders. So estrogens and testosterone. Both males and females have both hormones, just in different amounts. Males make more testosterone, females make more estrogens, but they're present in both sexes. These are the largest factor of bone growth during puberty. So here's the overall picture. When we're children, right after we're born, growth hormone and insulin-like growth factors influence our steady growth until we hit puberty. And it's not that this hormone goes away, it's no longer secreted. It's that sex hormones, these two steroid hormones, just pour into our system during puberty, estrogens and testosterone, and they account for that really quick, what you and I call a growth spurt during puberty. So these are responsible, I'll just remind you of that, for that growth spurt. All right, we're getting close to the end. I'm going to talk about stages of bone repair and then some diseases. Almost finished. So in terms of bone fracture, there is actually a table in your book in chapter 6 that outlines the different types of fractures. I'm pausing because I think it's table 6.2. So take a look at that, please. And it classifies bone fractures. Not that it's not important that I don't talk about each and every one of them, but then I won't be able to get to diseases of the bone and aging of the bone if I spend a long time on this. They're basically, the fracture types are based on whether or not the fracture goes all the way through the bone, how many pieces result from that breakage, yada, yada, yada. They're also based on, they're named also on the position of the bone after the fracture, whether or not the bones are aligned, misaligned, protruding through the skin in a compound fracture. So just look at table 6.2, please, when you get a chance. That explains the most common types of fractures in the human body. I'm going to mostly go over repair now, the process of repair once a fracture occurs. And it's just, there's stages. I'm going to number them similarly to your book. Right after a fracture, here's what happens. It's the formation of a bone hematoma. That's the title of this particular stage or phase. Hematoma just means blood clot, clotted blood from injured vessels. So in the area of bone breakage, any vessel that was damaged and leaks blood, that blood then clots and a hematoma forms. It's called a bony or a bone hematoma. We also get inflammation. That's one of the first things that happens is the area becomes inflamed and we get lots of swelling. That means increased vasodilation, bringing fluid into that area. That's what causes the puffiness and the pain as well. And during this stage, phagocytes, mostly macrophages, but some osteoclasts as well, they start to devour or clean up the debris. So cells die, both bone cells and blood cells. So this is the initial trauma stage. This may last for hours, days, even depending on the severity of the fracture, maybe even longer than days. Then what starts to happen is phase or stage 2. Fibrocartilage develops into something called a fibrocartilage callus forms. So during this stage, I'm going to draw a broken bone over here. We'll make it aligned. So blood vessels have ruptured. Leaked blood has created a hematoma. Inflammation ensues. Macrophages come in and osteoclasts and clean up the debris. The fibrocartilage business, I'm just going to get rid of my blood vessels here. Then typically what happens after phase 1 or stage 1 is, I'm going to use blue, fibroblasts in this area start to secrete fibers, and fibrocartilage forms in a callus formation. It's like a splint, almost like a bridge between the two broken bones. That's what this describes. So we get an increase in fibroblast activity. And it depends on, these are not set stages. While some of this is going on, we get the beginning of this, and while the end of this is happening, we get the beginning of stage 3, which is termed a bony callus, just takes over the spot of the fibrocartilage. So I'm just going to write bony callus forms. So this fibrocartilage bridge then gets replaced by actual ossification or bone tissue. What do we need for bone? Blood supply, bringing calcium, osteoblasts in this area, some mesenchymal cells and perichondral cells and periosteal cells in this, they differentiate into osteoblasts. So they start to secrete their stuff, mixes with the calcium, and we get a hardening of this tissue. That bony callus then replaces the fibrocallus. And this lasts weeks, sometimes even months. So I'm going to draw now a bony callus that's repaired, started to repair this area. And we end up with something sort of like this. Just give me a moment to correct my drawing. A full repair then tends to take on a shape like this. And during the bony callus formation, spongy bone tissue is what is formed. It always forms first before compact bone. Then stage 4 involves bone remodeling, and compact bone replaces spongy bone tissue. I just didn't draw the spongy bone for saving of time. This stage, bone remodeling of conversion of spongy bone to compact bone, can last up to a year. And we end up with something like I've drawn over on your left. Notice that this new bone tissue is thicker. It's also a bit sturdier and firmer. So never is a really strong word, but we almost never break a bone in the same place, in the exact same place twice. And the reason is because this new tissue is stronger than the older tissue. And should this bone be subjected to a large amount of stress in the future, the bone is going to break here or here in the older bone tissue before it breaks here. All right, we're getting close to the end. I'm going to briefly talk about bone diseases. We've all heard of this one, osteoporosis. This is actually a severe form of a condition called osteopenia, which is the normal thinning of bone tissue or bones as we age. So I don't know why your book doesn't mention osteopenia anymore. They used to. But osteoporosis really refers to an extreme form of that osteopenia in which bone integrity is compromised due to the thinness and brittleness of the bones. So this affects the elderly, and in general, as we age, osteoblast activity tends to slow down in the human body. That's largely hormonally regulated. As our steroid hormones drop as we age, osteoblast activity slows way down. But osteoclast activity keeps chugging right along. And so our bones tend to thin as we age. Women are at much higher risk than men, and that's due to the effects of estrogens are more potent on osteoblasts than the effects of testosterone. So particularly in women that are postmenopausal, because their estrogen secretions go way down, And that decrease in estrogen secretion slows their osteoblast activity. That thins their bones dramatically. I think that the figures are something like 30% of, or 70% of women who reach age 80 have some form of osteoporosis. And women can lose something like 8% of bone mass per decade after their mid-40s. So it's significant. Males are subject to the same thinning of bones, just not to the same degree. I think the male numbers are something like 3% per decade after age 60. So it's not nearly as common or severe in men as in women. And which makes it extra difficult for women. Typically, women's bones are not as thick as males to begin with. So they kind of get a double whammy there. Typically, it affects it's called the vertebral body of the vertebrae. It also affects areas of the femur, hence the common broken hip in people with osteoporosis. The neck of the femur bears a lot of weight and it tends to thin and either crack or break. Treatments for this are variable. Calcium supplementation is nothing, it's good, but it's not a cure. It's nothing more than a supplementation. So calcium supplements definitely are necessary and recommended for postmenopausal women just to ensure that they get adequate calcium in their diet. Because as you know now, without calcium, we can't make good, healthy bone tissue. Estrogen therapies are effective. So it's called estrogen replacement therapy. Those are very effective. Unfortunately, they have deleterious side effects. So estrogen therapies are effective on increasing osteoblast activity, but it's not really recommended because of the negative side effects of estrogen therapy, which is increased heart disease, increased chance of breast cancer, stroke. There is, see if I can spell this correctly, bisphosphonates is a group of drugs that are proven quite effective. What these do is they decrease osteoclast activity to help slow down that bone degradation. So exercise is good, high calcium diet is good, and what the literature says too, I know it's too late for most of us because we're all fully grown, but as we are growing, the more exercise we can get while we're growing gives us a thicker bone mass to begin with, so that when old age sets in, we have more to work with, more to lose before we get breakage and compensation. I wanted to mention Paget's disease. This is, when I see this term, this is not super accurate, but I always think this is the opposite of osteoporosis. Rather than degradation or loss of bone mass, Paget's disease, which afflicts middle-aged to older people, it's very uncommon in young people. This is sort of like the abnormal growth of bone tissue. That might not sound like a bad thing, but the tissue is not necessarily healthy. It's typically spongy bone tissue, no matter where it grows. It's not very structurally sound. This disease can be quite painful. It's not fully understood why this condition exists. And it can affect anywhere on the body, any part of the skeleton. But the common places are like the vertebrae, the pelvis, the femur, the tibia, and it's called Paget. This abnormal bone tissue that grows on the bone is called Pagetic bone. last but not least, osteomalacia. This just describes bones that are poorly mineralized. We don't get enough mineralization in the ossification process. You've probably heard of the term rickets, which affects young children. This is poorly mineralized bones in children specifically. The deformity describes bones that are quite deformed, like bowed legs, large non-fusing epiphyseal plates. And it's from inadequate calcium mostly, or calcium phosphates being deposited into the bone. So the bones are weak and malformed. This is largely, last thing I'm going to say is this is largely due to a vitamin D deficiency can contribute to this as well. Not just a lack of calcium in the diet. All right, guys, we made it. I'm going to cut my recording here.